Is it okay?
Yes, sir.
Okay, welcome to today's topic, deflection of prestressed concrete beams. There are several reasons for deflection. One is deflection at transfer of prestress, that is due to prestressing force and dead load. During the transfer of prestress, dead load is there. Okay. Second one is short-term deflection, that is due to above deflection, that is prestressing force, dead load, and with external load, that is live load. Long-term deflection is a time-dependent deflection, that is due to sustainable long-term live loads will create a creep. Okay. That creep effect will create a long-term deflection. That is the combination of prestressing force, dead load, live load, and as well as this creep. Here important thing is you have to understand how prestressing force will create a deflection for different cable profiles. For example, this is the first cable profile. Cable is concentric, means cable is provided at the axis of the beam. That means eccentricity is 0. This prestressing force will create a compression along the axis, not perpendicular to the length. We are calling deflection is perpendicular to the axis. Perpendicular to axis there is no deflection. That's why delta is 0. Second case is the same straight cable is provided with a constant eccentricity. The same cable is provided with the eccentricity. Now we can expect a deflection. You see the free body diagram of the force. Here if you transfer this P to the axis, it is having a force couple system, as you know in engineering mechanics. Here again P is axial force, it will not create any deflection. This moment will create a deflection. The deflection due to moment, there is a formula you already studied in strength of materials, that is ml square by 8a. This moment will create a upward deflection. Then come to third one. Here the triangular shape is there. The cable profile is a triangular shape. It is also called as harped shape. Actually we are going to provide the cable profile as per bending moment due to external loads. If the load is centrally point load, then the bending moment diagram is like this only. If you provide the cable follows the bending moment diagram, there is a load balancing concept. This cable profile will create a upward force. That upward force is equal to 2p sin theta. Because theta is small, we can take sin theta is tan theta. Tan theta is opposite by adjacent, that is E by L by 2. Because of eccentricity is 0 at the ends, there is no moment. Here actually P is there. This will not create any deflection. Only this will create a deflection, upward deflection. This is a point load. Actually this is due to cable profile. This much force will transfer to the concrete. Okay. That will create upward deflection. Again this is a point load at the center of the beam. You know the formula. A beam carrying central concentrated load, already studied, WL cube divided by 4080A. Okay. This is the deflection due to this type of cable profile. Then come to the same cable profile. Here some eccentricity is provided. Here P is there. Because of this eccentricity, there is a moment creation. And because of this cable profile, again upward force will be created, that is a point load, that is 2p tan theta. Here tan theta is now actually if you take, this is the triangular shape, this is actually E1 plus E2. Opposite is E1 plus E2, then the adjacent is L by 2. Tan theta will be E1 plus E2 by L by 2. M is this P into E2. P is actually, this is almost horizontal. It looks inclined, but theta is very small. Once theta is small, cos of that small angle is almost equal to 1p. That's why P into E2 is the moment. Here This is responsible for deflection, this is also responsible for deflection. This will create upward deflection, this will create a downward deflection. If more than two deflection comes different nature, we have to use sign convention. Downward deflection I will take a positive, upward deflection is a negative. This will create a downward deflection, it is positive. I am taking the ml square by 80A, and this is due to point load WLQ divided by 4080A. You can make it vice versa also, there is no problem. Then come to another profile. This is very similar to this case. Instead of the triangular shape, it is a curved shape, parabolic shape. Whenever the UDL is there, external load is UDL, you have to go with this shape. This will create a upward UDL, that is equal to 8 PE by L square. This you already studied in the load balancing concept. Because of this upward UDL, there is a upward deflection. You know the formula for deflection due to UDL, that is 5W L raised to 4 divided by 384 EI. Because of zero eccentricity, no moment here. Then the next one, similar case with eccentricity here. Because of this eccentricity, moment comes, and as usual, this upward force created because of this cable profile. Now eccentricity is total eccentricity, E1 plus E2 should be taken to find WC. Now again same convention I am using. Downward is positive, upward is negative. This will create a downward deflection ml squared by 80. This is upward deflection 5W L raised to 4 divided by 384 EI. That is about the discussion on deflection due to pre-stressing force. Actually that is very important because this is very new to you. The deflection due to self-weight and deflection due to live load you already studied in strength of materials. Deflection due to imposed loads, there are different types of imposed loads, but I am taking only two cases. One is central concentrated load, another one is UDL. You already studied in the previous discussion. This is central point load WLQ divided by 4080A. For UDL, imposed load, that is 5W L raised to 4 divided by 384 EI. This is about live loads. Discussion on deflection due to self-weight. Sometimes self-weight may be given. If it is not given, you have to calculate the self-weight. Usually all beams are prismatic beams. Prismatic beams means uniform cross section throughout. Finding self-weight is width into overall depth into 1 meter length into density of concrete 25. Suppose density of concrete is given, you take that value, otherwise you assume it as a 25 kilonewton per meter cube. The UDL you will get in kilonewton per meter. B and D should be in meter because this is kilonewton per meter cube and this is also meter. Again, the self-weight is a UDL. The formula is same as the above UDLs, 5W L raised to 4 divided by 384 EI. How to find long-term deflection? There is a formula found by Linz. Linz formula is long-term deflection equal to deflection due to dead load and live load. This is a positive value minus deflection due to pre-stressing forces multiplied by final pre-stressing force divided by initial pre-stressing force. Suppose loss of pre-stress is 15%, that PF will be 85%. This is 100%. 85 divided by 100 will become 0.85. This will become 0.85 if it is 15%. If it is 10%, it is 0.9. If it is 20%, it's 0.8. Okay. Instead of substituting what is PF, PI and all, just by knowing the loss of pre-stress, you can substitute this value like this. Then pi will be given, that is creep coefficient. Suppose pi is not given, you just leave it. This will become the long-term deflection. Then one usual question will be there always. What are the factors affecting the deflection? If you see all the formulas, you can easily identify which are all the factors affecting the deflection. One is external loads. You see, all external loads will influence the deflection. Then span of the beam. Then Young's modulus. Young's modulus is depending upon the characteristic strength of concrete. Then moment of inertia. Moment of inertia is depending upon cross section. It may be a rectangular, L section, I section. Okay. Moment of inertia. Then if you see this formula, here P is important, M is P into E, here 2P sine theta. Prestressing force is important, that also influence for deflection, and eccentricity of the cable will influence on deflection. Just by referring the formula you can answer that one. There will be always a question, what are the factors influencing or effects on the deflection. Some 5-6 factors you have to write. Okay, thank you.